esters can be created via FGI, which includes oxidations and substitutions. Substitutions can be acyl or SN2. Even one can achieve this. The acidity of the alpha protons can be used or explored exploited, I should say, to functionalize esters at the alpha carbon. Okay. So here, let us first synthesize or consider synthesis of esters via FGI. Now let me say that the most common way to synthesize an ester is by substitution reaction. Esters of the type RCO2R prime can be synthesized from carboxylic acids such as RCOH, and it will involve the acyl substitution in which the OH will be acting as a leaving group and will be replaced by OR. So suppose we wanted to synthesize an ester of the type like this, and we can do this. How? We can think that we are using one acid of the type like this, and we are using R prime O minus, and that will be basically replacing the OH group, and our ester will be formed. Now if you want to achieve these type of reactions, the best way is over here to achieve the reaction using, so I'm giving you the best method, which is basically using the acid chloride, that is RCOCl, okay, which can obviously be made from the acid, that is RCOH. Here the base is the pyridine. Our acid chloride is formed. Now you react this acid chloride with the alcohol, that is R prime OH, and that will give you your desired ester. So this is the best method. Alternatively, the other method that we can use is called the Fischer Esterification, and this basically involves the acid catalyzed reaction of carboxylic acid with an alcohol. Now, it is worthwhile to mention that since the OH and the OR have similar leaving group ability, okay, the reaction is driven forward by using excess of alcohol then also via removal of water or by removal of ester product as it is formed such as by only using distillation techniques. Okay. So basically what we are trying to do over here, we have acid, we have the alcohol, we are using catalytic amounts of concentrated sulfuric acid, and that is giving us our ester along with the formation of water. So either you remove this product or you remove this product to take the reaction in the forward direction. That is what we are trying to say. Next thing, can we think of other methods by which an ester can be formed? So let's say this is procedure number 3. We have discussed procedure number 2, and what I called as the best method was the procedure number 1. Okay. Now out here we can think of a reaction of a carboxylate nucleophile, okay, that is RCO2 minus with an alkyl halide. Let's call it as R prime X. Okay. Also gives ester RCOO prime. So rather than having a substitution at the acyl carbon as we did in procedure number 1 and 2, the reaction over here involves, let's say, reaction involves over here a backside attack of oxygen nucleophile on an alkyl halide. You can say this is very much analogous to Williamson ether synthesis type of procedure. Since the reaction is SN2 type, it requires a good leaving group. Okay. That is, we have to use a halide or a tosylate. That is our OTS. And an unhindered carbon, because SN2 is favorable at either methyl primary or secondary alkyl halides. Now, why we are using a unhindered carbon? What is the reason behind it? The reaction can be especially slow if there is any steric hindrance since the nucleophile is a resonance stabilized, that is the carboxylate is resonance stabilized, so it is a weak nucleophile. It is resonance stabilized, so we will say it is not strongly nucleophilic. That is the first part. And the carboxylate is also not strongly basic. Okay, so these are the reasons. All right, now, so if we have a carboxylate ion, if you have a carboxylic acid, we will react it with a base, and that will give us our desired carboxylate ion. And we will have the alkyl halide, which is the R prime X, that will make a nucleophilic attack, and we will get our desired ester. And as we have discussed, that this particular alkyl halide, the alkyl group has to be either a methyl (1 degree) or 2 degree, and the X has to be a good leaving group. Another way of making ester, which we are discussing over here at procedure number 4, is making methyl esters. Okay, these can be prepared with the reagent called diazomethane, that is CH2N2. So when reacted with carboxylic acids, carboxylic acids diazomethane becomes protonated and serves as an extremely good reactive electrophile. Why so? Since it contains an extremely good leaving group, which is our N2. So how is this taking place? So we will show you that. We have the carboxylic acid, we are using CH2N2, and that leads to the formation of a methyl ester. So out here mechanistically one can show that we have the acid group over here. Our diazomethane is as shown, takes up the proton, initially acting as a base. So in this step we are basically deprotonating the carboxylic acid, leading to the formation of a carboxylate ion. That becomes our new nucleophile. After taking the proton, we have a molecule which is CH3 and joined to the N2, which is our nitrogen. Now CH3 becomes highly electrophilic because nitrogen is a good leaving group. So any attack over the CH3 by a nucleophile leads to the replacement of the N2 via the SN2 procedure and gives us our desired methyl ester. Besides this, another procedure of making ester, which is our fifth procedure over here, will be the oxidation of ketones using the peroxy acid over here. That is, we can either use a MCPBA, that is metachloroperbenzoic acid, or we can use the trifluoro peroxyacetic acid. This is basically a Bayer vinegar oxidation process, and it is used especially for the preparation of cyclic esters, which are known as lactones. From cyclic ketones. So suppose we have the RCOR prime. We are using a peroxy acid. The R group, that is or let's say the alkyl group, that is more substituted migrates. Okay. So if here we say R prime is more substituted, then what will happen? This will migrate. All right. Now, if we wanted to show the reaction for a cyclic ketone, this end is less substituted, that end is more substituted. So now if you are using a MCPBA, so the O will enter over here. And that means, what is going to be the structure of the ester? This will be the structure of the ester or the lactone that we are making out here. And this is our cyclic ketone. So that completes the entire synthetic procedures that one can use to make the acid derivatives. Okay. And in the next part of the lecture, as we have been doing, we will be using or talking about the retrosynthesis procedures of the acid chloride acid derivatives. So keep visiting the lecture series on synthesis and retrosynthesis of organic compounds. This is Dr. Sarkar over here saying goodbye and have a great day.